Good morning. Again, my name is Thomas Graff. I'm the training manager for energy recovery. So let me go ahead and share my screen here. All right. Okay, so reclaiming high pressure energy from the CO2 system. So what we're going to talk about today is how energy recovery has designed the pressure exchanger, our PX G1300, to enable CO2 refrigeration systems to recover energy that normally would have been lost and improve the efficiency and reduce the energy usage. Uh, we believe that the adoption of this technology in the CO2 transcritical booster systems can help make it more attractive to those customers that are maybe on the fence about switching to CO2 because of its high energy requirement. So let me next slide here. Okay, so for my topics for today, not getting too complicated. First, I just want to talk a little bit about energy recovery. Where did the pressure exchanger come from? What's the technology based on? Then we'll get into exactly how does the PX G1300 work? Okay, what's inside it and how does it accomplish these objectives? And then we'll get into integrating the PXG into a rack system and what are the benefits to that. So a little bit about energy recovery's background. It's not a new company. We've been around for over 30 years in the desalination industry. Uh, Energy recovery got its start in the reverse osmosis process. For those of you that are not familiar with it, there's basically two methods of desalinating water. You've got either the distillation process where you're going to add a lot of heat energy and bring that water to a boil, convert the water to steam, and then condense that steam back into a liquid without any of those impurities in it. Okay, so that it'd be drinkable. The other method is called the reverse osmosis process. In that process, you're going to pump up the pressure of that seawater and force it through a membrane. Okay, so some portion of that fluid will go through the membrane and become, drinkable water. Still, a lot of that water is rejected by the membrane, but it's still at high pressure. And typically, what was done was that water would just be dumped back into the ocean. Okay, so with the pressure exchanger, we can capture that wastewater that's rejected by the membrane, okay, and capture the energy that's trapped in it and convert that pressure to another fluid. So we'll pick up fresh seawater, okay, and transfer that pressure to the fresh seawater, and then send it to an auxiliary pump to raise the pressure up just a little bit more so that we can put it right back into the flow going back into the membrane. So we get to reuse that energy. Okay. At this point, companies that are considering construction of desalination plants, it's almost unfathomable to do that without this technology. It usually gets about a 60% energy return. Okay? So there are a lot of facilities that are using the pressure exchanger for the desalination industry. And as of 2019, Energy Recovery had shipped over 20,000 pressure exchangers. And since then, I believe we are up to over 30,000. So just in the last 5 years, we've added, shipped an additional 10,000 units. So the technology is solid, and it's well known in the water industry. So in right around 2020, 2021, we were approached by the Department of Energy. And we were asked if this same technology could be applied to the CO2 industry. So we started investigating. And what we came up with in 2022 is the PX G1300, which enables us to capture that same pressure loss that we see in the high pressure uh, expansion valve. Okay? So, uh, 2022, we introduced the PXG, okay, and just last year and earlier this year, you may have seen in some of the trade publications, we're already receiving acclaim for that invention with several awards. So how does it work? Well, what you're looking at here is an animation of the ceramic cartridge that's inside the PX. Now, I've removed the rotor, which would be in between these two end covers. Okay, so as we bring in a low pressure refrigerant, low pressure vapor, it's going to fill up the ducts. That duct will rotate around from the low side of the PX to the high side, and then we're going to expose it to the high pressure fluid, that transcritical fluid, which is going to act almost like a liquid piston and compress that vapor and send it out where we can do more work with it. Okay. And then as it does that, that high pressure fluid transfers its energy and then begins to expand. Okay. Once it gets back over to the low side of the system, that low pressure vapor pushes it out. So that saturated mixture gets pushed out to the flash tank. And I'll get into more detail of that in some upcoming slides. Okay. So here I've got a cross section of the PX. Okay, and when we look at the PX, we kind of divide it in half vertically. The left side of that, as you're looking at that diagram, is considered the high side of the pressure exchanger, while the right would be the low side with our low pressure in and out, and our on the left the high pressure in and out. We also divide it in half horizontally, with the top half of the rotor acting as a compressor, providing that exchange of pressure, and the bottom half acting as the expansion valve. So you're really getting two components in one. You're getting some free compression, and you're getting the expansion that's needed for the refrigerant process. Okay. One of the benefits of this design is that there's no superheat required. You know, you can see here the that light blue color, that cyan color, represents a superheated vapor. Okay, it could be a saturated mixture, as what we've got coming in LP out, or even a supercritical fluid. So whether it's supercritical, saturated mixture, superheated vapor, the PX can handle all of those phases. So in normal operation of the refrigeration system, the PX G1300 saves energy, reduces water usage, and provides operational flexibility. In conditions when a refrigeration system is forced to operate beyond its design temperature point, the PX G1300 provides additional capacity and high temperature rack stability. Okay. So how do we do that? Well, here is what we've got inside the PX. So the outside of it is a stainless steel shell, okay? And inside we have an alumina silicate ceramic. Okay? That ceramic cartridge consists of two end covers, which are stationary, and then a sleeve, which is also stationary. And inside that sleeve and sandwiched between the end covers is our rotor. The only moving part inside the PX is that rotor. Okay, and that's going to operate inside those ceramic pieces with a gap of a few microns. Okay, so that gap is going to be filled with the high pressure CO2. So that means the rotor is going to operate in that CO2 envelope, almost like a hockey puck on top of an air hockey table. it's never going to touch the sleeve or the end covers. So as that rotor is spinning inside that cartridge, it's not making contact with the sleeve or the end covers. So that means there's almost no friction. So what's not pictured here is an electric motor that's mounted to the bottom of the PX. So that motor, all it's doing is rotating the rotor so that the ducts move from the low side to the high side. But since there's almost no resistance, that motor takes up almost no energy. We're talking less than 0.1 kilowatt. Okay. Now, if we take that rotor and we kind of fillet it and lay it out flat, you'll see several ducts that run the length of the rotor. Okay. And what I'd like to do is just kind of walk you through what happens as each of those ducts passes from the low side to the high side and then back to the high side. So here we can see the low side of the rotor, the low side of the PX. So in our first duct here, okay, we've got a saturated mixture. The high pressure transcritical fluid has already expanded, and we've got a saturated mixture. And now the duct is going to rotate around to the low side of the system. As it rotates in position 2, it's going to be exposed to the opening in the end covers. Okay, we call those openings kidneys because they're kind of kidney shaped in our original designs. So as we come past the opening in those kidneys, we're going to allow the low pressure vapor, okay, low pressure. Now, I say low pressure, but it's 590 psi, so it's not low pressure as you'd consider with the more traditional refrigerants, but with CO2, it would be considered lower pressure. So we're going to fill up that duct with this low pressure vapor. It's going to push the saturated mixture that's already inside that duct. It's going to push it out the LP out kidney. Okay, and we'll take that saturated mixture and deliver it to the flash tank. Okay, in position 3, more of that vapor is brought in and pushes out the saturated mixture so that by position 4, the entire duct is filled with that low pressure vapor and all of the saturated mixture has been pushed out to the flash tank. At this point, the rotor continues to move around and it's going to transition past the dividing point into the high pressure side. Okay, so it's going to be positioned in between those kidneys, so it's going to seal it off and then transfer it to the high side of the system. When it gets to the high side of the system in duct position, I believe that's 6 here, it's going to be exposed to the high pressure kidney openings. When it does, that transcritical fluid coming from the gas cooler is going to enter the duct. Now that transcritical fluid, we've removed some heat from it in the gas cooler, so we've made it more dense. Even though it's not a fluid, it's going to be more dense and liquid-like. So compared to the vapor that's in there, it's going to hit that vapor almost like a liquid piston and compress that vapor. So as it continues to enter the duct in position 7, it's going to compress that vapor until it's almost at the same pressure, a little bit less, okay? And then it's going to exit the PX through HP out, and we'll take that to do additional work, remove more heat from it. Okay? As the last of that vapor is compressed and pushed out, the remaining transcritical fluid will have expanded inside that duct. And at this point, it's going to transition past the opening in the HP out kidneys and be brought over to the low side of the system where it will start this process all over again. So as we look at this, you can see the top half of the rotor acts almost like a compressor. It's going to have that low pressure vapor enter. Okay? And then as the high pressure fluid comes in, it's going to compress that vapor and push it out. The bottom half acts like an expansion valve. Our high pressure transcritical fluid is going to enter the ducts. As it expands, it moves around to the low side, and that expanded saturated mixture now will be pushed out to our flash tank. So we get both compression and expansion in the same device. And again, we're only using, less than 0.1 kilowatt to do that. So now let's take a look at how we integrate that into the rack system. Okay. Well, one of the hurdles that we've got with CO2 is the high ambient conditions, is the buildup of pressure in the flash tank. So as our ambient starts to rise, that means the pressure and heat energy that's in our refrigerant going through our gas cooler is still going to be fairly high. So when we come to our expansion valve, we're going to have a lot of heat energy still trapped in that refrigerant. When we go through the expansion valve, we allow that refrigerant to expand, but that heat energy is still there. And what happens is that heat energy causes some of that refrigerant to instantly boil off. We refer to that as flash gas. So that means instead of bringing mostly liquid, we're bringing liquid and a lot of extra vapor into the flash tank. So with that vapor means we're going to have higher pressures in the flash tank. In order to compensate for that, our transcritical booster system is going to open the flash gas bypass valve. When that happens, some of that vapor then is brought to the MT compressors, those medium temperature compressors, and forces the MT compressor to compress that refrigerant. Now, the refrigerant that was brought, it's not doing any work for us. It didn't pick up any refrigerant out of our cases. It's not removing any heat from the frozen section or the produce section. Okay, but we're still having to compress it. So then we end up with a cycle of a small portion of refrigerant that's continuously compressed, had heat removed from it, expands, and then goes through the bypass valve all to do it all over again continuously. As long as we've got those higher ambients, then more and more of this pressure forces the MT compressor to work even harder. Okay, so our solution is to add the energy optimizer to the rack, okay, at the gas cooler return line and in between the high pressure valve and the flash tank. When we do that, we're going to take that the supercritical fluid, we're going to bring that into a subcooler. Inside that subcooler, we're going to remove some of that heat energy, some more of it, okay, which is going to drop the temperature of our fluid as it comes to the pressure exchanger. It's going to enter the pressure exchanger at the high pressure in port. Okay. It's going to fill the duct. As it fills that duct, it's going to compress the vapor, but I'll get into that in a second. As it compresses the vapor, it's also going to expand as it rotates from the high side over to the low side. By the time it gets to the opening in the end cover, the kidney opening, it will have expanded to a saturated mixture. Now, a saturated mixture, because we removed all of this extra heat, is going to be lower in flash gas. So we're going to have a higher percentage of liquid coming out of LP out. And we're going to deliver that to the flash tank. Okay. Meanwhile, back at the subcooler, we teed off of our incoming line a small portion of that refrigerant. We're going to pass that through the subcooler expansion valve. Okay. As it expands, we're going to drop it to a saturated mixture, bring that into the subcooler, and that's what's going to absorb the heat from our refrigerant that's passing through it, from that supercritical fluid. As it absorbs that heat, it's going to boil off into a vapor. That lower pressure vapor is going to be brought to our PX at LP in. Okay, now you notice LP in is at about 590 psi. versus the 551 that we've got at our flash tank. Okay, now we have to have that pressure differential at the PX because the PX doesn't suck. Okay, and I mean that literally. It uses the pressure differential to move the refrigerant in and out of it. Okay, it will not create a low pressure area like a reciprocating compressor would, or one of the screw compressors or scroll compressors. Right, so we have to have that pressure differential. That's what's going to push that refrigerant out. So as it enters the ducts in our rotor, it'll push that saturated mixture out, okay, and then transition from the low side over to the high side. When it sees the high side opening of the kidney, that supercritical fluid is going to compress it. Again, because we've removed even more heat from that supercritical fluid, it's gotten even more dense. So that means when it comes HP in, it's going to act just like a liquid piston and compress that vapor. So we're going to transfer that pressure from one fluid to the other. Okay, there's a little bit of loss there, as you can see. 1,139 psi versus 1150. And the reason, well, because of that, we're not going to be able to bring it right back to the gas cooler. Okay, if we pipe that from the PX back into the gas cooler, well, that would make it a perpetual motion machine. And if that were the case, we'd have a whole lot more awards than what you saw in my first couple of slides. Okay, so because there is some loss there, we've got to take that to a secondary heat exchanger. Okay, so we'll pipe that to an auxiliary heat exchanger. Now you can either use an auxiliary gas cooler or a water-cooled condenser and a water tower, whatever the customer wants. Ideally, if you were doing this as a new installation, if you could specify a gas cooler with 2 circuits, you could pipe it right back to the same gas cooler, use the same fans, use the same controls, and only have one crane pick when you install it. Right? But it does have to be in a separate circuit. So we're going to pass that refrigerant into our auxiliary gas cooler, or the secondary circuit of our primary gas cooler, blow the cooler ambient air across it, remove some heat, and then we're going to bring that supercritical refrigerant back to the energy optimizer to an auxiliary high pressure expansion valve, where we're going to allow that refrigerant to expand and be brought back to a saturated mixture. Now, as we look at this, when we come out of the gas cooler, we're taking a small portion of that refrigerant, a small portion of that flow out to go through our expansion valve. Okay, now that does reduce the volume of refrigerant you're passing through it, but because we've removed so much more heat, we're getting so much less flash gas that the amount of liquid still ends up being about the same as what we would get as if we pass it through the high pressure expansion valve. But everything coming through the auxiliary high pressure expansion valve ends up being extra. So all of this saturated mixture coming out of here into our flash tank ends up being extra. So that extra liquid is where we get the bonus. Okay, and again, we got all of that for free from the pressure exchanger because the energy that's required to move those ducts from one side to the other is minimal. Okay, so now let's add the energy optimizer's refrigerant flow to the rack and look at how it changes the flow on the pressure enthalpy diagram. We're going to start off at position 1 here, which is just the gas cooler. We'll take that refrigerant, bring it into our subcooler. That's going to remove more heat. So we're going to move our line a little bit further to the left because we've got less heat. From there, we're going to enter the PX, allow that refrigerant to expand, which will drop the pressure. At 0.3, it'll be a saturated mixture, and we're going to deliver that refrigerant to the flash tank just like the standard rack system. Okay. Now we come back up here to 0.4. Okay, we're going to pass it through our subcooler expansion valve. That's going to drop the pressure again to 0.5. We'll pass it through our subcooler. We're going to remove or add heat to it now. We're going to remove it from the main refrigerant line and add it to our boiling refrigerant. That'll boil off all of the liquid. We'll have vapor coming out of the subcooler at 0.6, where it's going to enter our pressure exchanger. Now, once that enters a pressure exchanger, we're going to raise its pressure. Now, with a typical compressor, that line leans to the right because we've got the added heat of compression there. So you would expect this line to go straight up at this point since there's no heat of compression, when in fact, it's going to incline to the left because what it does is it follows our temperature lines here. It's going to follow that curved temperature line. It's going to go up slightly because of the minute amount of mixing that occurs, but not substantially. The other thing that you're going to notice is that line doesn't come all the way up to the same line as our gas cooler. Okay, because like I said before, we're not a perpetual motion machine. We can't take refrigerant out of the gas cooler, do some work with it, and then put it back in the gas cooler at the same pressure. So it's going to have to go to our auxiliary gas cooler. There, we're going to remove more heat from it and bring it back to the energy optimizer to go through our auxiliary expansion valve. Okay, that drops it down into a saturated mixture, and then we bring that back into our flash tank. Okay. So by adding the energy optimizer to the system, we remove more of the residual heat energy in that subcooler. Okay. That means we're going to have less flash gas generated during the expansion inside the PX. So the saturated mixture flowing to the flash tank will have less vapor. Okay. Even with the small amount of refrigerant used to cool the subcooler, the PX is still delivering about the same amount of liquid to the flash tank as the HPV. But we all are also using the PX, the auxiliary gas cooler, and the auxiliary HPV to get even more liquid to supply to the flash tank. So the result is we're supplying more liquid and less vapor to the flash tank, reducing the flash tank pressure, which means the bypass valve doesn't have to open as much, which means the empty compressors don't have to work as hard. Not only are we using less energy, it also means the empty compressors don't have to work as hard, which should extend the life of the compressors. Integration is easy with the energy optimizer. Whether we're talking about a new installation or retrofit, okay, the energy optimizer is only going to take up about 2 by 2 by 4 foot high space in the mechanical room. So we're going to connect that at the return line from the gas cooler. We're going to tee into it there before the high pressure valve and just before the flash tank, but after the high pressure valve is where we're going to return that saturated mixture from the PX. Okay. So to kind of summarize PX, it's got an easy integration into both new and existing systems. 4 mechanical connections, 2 for the auxiliary gas cooler, the supply and return, and then the 2 points that I just showed you where it connects to the existing rack system. So the rack only needs to be down for a minimal amount of time while you raise in those 2 T connections. Okay. It's got a very compact footprint. Like I said, about 2 feet wide by 2 feet wide by about 4 feet high. And it's compatible with almost all commercial refrigeration controllers. And at that point, let me go ahead and turn it over for any questions we might have.